Okay, good afternoon, everyone. So slowly making our way through this unit. I think we might finish it today. One of the things we talked about last time was a whole bunch of different convolutional neural networks as they evolved through the years. And one of the ones we talked about was VGG. And this, as I said before, still remains a respected network. It's still used to generate features for a lot of other tasks. And so what we can do next is we can take a look at some of those features, or at least how we extract them in PyTorch. So the Torch Vision package is the one that you can download with all the pre-trained models. And here you see that VGG16 is among them. And when you instantiate that model, you can select pre-trained equals true, which downloads all the weights. So you can just use the network yourself. And if you do print string model, it gives you a nice overview of how the network is constructed. So you can see that they've broken it up into three sections. There's the features section, the classifier section, and the average pool section between them. So the features section, if you notice, these are all convolutions, like convolution ReLU max pool. But it shows you all the details. It shows you like the very first convolutional layer. It's 2D convolution, starts at 3 channels, goes to 64, 3 by 3 kernels. Stride is 1, which means no downsampling. And padding equals 1 with a 3 by 3 kernel would give you the same style of padding, and so on. So you can see exactly how the network is constructed. And then when you look at the classifier part, you can see that this is just an MLP. You have linear layers. These are dense layers, ReLU, dropout, linear, ReLU, dropout, and then linear, and then that's it. And as you can see, the last linear layer outputs 1,000 features. And that makes sense because this is for 1,000 class ImageNet. Another thing you can notice is that the number of features that are coming into the first dense layer is 25,088, and that's a fixed number. What is not fixed is if I put in different images into this network, different sized images, then because these are all convolutional, essentially, like if I put in an image that's half as big as an internet 224 by 224, then what comes out of this final convolutional layer will be also half the size, half the dimensions of an internet image, ImageNet image. So the average pool layer is meant to bridge that gap, and this allows you to put in images of any size you want here, so that basically the average pool layer will do average pooling. It's called adaptive average pooling, so that spatially the output is 7 by 7. And then this number, 25088, is actually 7 times 7 times 512. So it's not obvious because it's been blanked out here, but basically the number of channels coming out of the features section, there's 512 channels. So that's why the average pool layer needs to adjust its output size to 7 by 7 so that the total number of features is 25,088. Okay, so that's the reason why you can use these networks with any size images you want. It will just automatically adjust the spatial dimensions so that the classifier input is the right dimension. Is that making sense? Any questions on that? Okay. Yeah, so you can see exactly how everything is constructed here. And what we can do is, this is done in one of the demos, and it's also going to be used in the lab, is you can get you can get an API key for Flickr, which is a photo hosting site, and then you can download images by keyword. The details are in this demo, but so for example, in Flickr, if we put in the keyword elephants, then we get all sorts of images like these ones, and these are not very high resolution. I probably adjusted them so they were not very high res for the demo. But basically all we need to do is make sure that we have separate test and train directories, and then within each of those that we have separate subdirectories for the classes. And for this particular demo, there's only going to be the elephants class. We don't really have more than one class because all we're going to do in this demo is look at the feature maps. We're not going to do any classification directly. So that's how we can set things up. Once we have things set up that way, then we can use the image folder function in PyTorch to create that dataset object. And we do have to do one thing that's sort of important, which is anytime you use one of these ImageNet networks, you want to make sure that your images are normalized in the right way in each of the channels, red, green, blue. And this was something that was decided a while back. I don't know who decided it, but basically all these networks are set up to work with particular means and variances in each of these subchannels. So this is what we're going to do. We're going to normalize our pixels to have this mean and standard deviation in each of the channels. That is going to be one of the transforms. It's actually, let's see, what else are we doing? So we're going to, this is kind of in the order of what we're going to do. First, we're going to crop the images to size 224 by 224. But if you want to do a different size, you would just change that number there. Then we're going to transform our data to tensor format, which we need to work with PyTorch. And then finally, we're going to normalize it, and this is how we've built our little normalizing function. So this is what, these are like, this is also where if you were doing feature augmentations, image augmentations, you would add them to this list. So this is what's going to happen to the data. Any new image that comes in, these things will be done to it. And then we set up our data set. We set up our data loader. Batch size 10 here, we're just going to play with 10 images. And let's see what happens if we take a batch of 10 images, put it through our model. And this is going to give us 1,000 linear scores. These are 1,000 real numbers. So we're going to put that through a softmax layer to turn that into probabilities for each of those images. So then we have a PMF. And then we're going to use this topk command to look at the, basically like extract the top 3 classes for each one of those images. And once we know those top 3 classes, we can consult a lookup table that corresponds to ImageNet, and it knows, let's say, maybe the class was like 746, and that corresponds to an African elephant. So there's a lookup table. I didn't show the code here, but it's in the demo. And from those top 3 classes for this image sample 0, you can see that it's 70% sure that it's an African elephant, 28% that it's a tusker, and about 2% that it's an Indian elephant. So it's doing quite a good job. All of these are types of elephants, and you can see it's pretty confident in these soft class labels. And that remains true for all 10 images in our data set. I think all of them, it's either African, Indian, or tusker elephants. So it seems like these pre-trained weights are working pretty well. We're downloading images that are not part of ImageNet. They're just coming from Flickr. put them through the network, and this is correctly classifying them among those 1,000 ImageNet classes as reasonable choices. Okay, is that making sense? All right, any questions? Yeah.
So when we say mean of the images in the red channel, blue channel, and the green channel across the data set, is it the mean of the red channel in that particular image?
Oh, are you talking about this?
Yeah.
Yeah, so that's the mean of the red channel pixels. So there's 224 squared pixels. They have this mean and this variance.
Yeah, like that is for each image or across the data set?
I believe it's for each image. Yeah, we need to look up the documentation, but it really makes sense that it's going to do this for any image it gets.
Mm-hmm.
It's going to do this normalization on that image.
Yeah, that's what, like if any image comes in, it subtracts the mean and divides by standard deviation. That particular mean
Is across the pixels.
Okay.
Right? We have a lot of pixels. Each image has a lot of pixels, like maybe, tens of thousands, maybe even 1 million pixels, depending on how big it is. Yeah, so there's plenty of samples from which to calculate a mean just from one image. Yeah. Yeah. Okay, great. Any other questions? Okay, so so that's just sort of verifying that yes, this pre-trained model is working. And then another thing we can do is we can actually look inside the network. And so we built a little function here that what it does is you give it a list of which feature layers you want to extract the outputs of, so you can look at them, and which classifier layers. And then you give it the model as well. And then what it does is it will take a sample in, and you can see it has empty lists for feature outputs and classifier outputs, and it will go through the feature modules one by one. And if it sees that this particular feature layer is in the list of layers that you want to keep, it will take the outputs of that layer and it will just combine them or add them to its growing list. So it goes through all the feature modules one by one, processing and keeping the ones that you want to look at. And then it goes through the average pool module, and finally the classifier modules. And for the classifier ones, also any ones that you want to look at, it will keep. And so here's where we'll use it, just to take a quick look inside this network. So what I'm showing here is one particular image. This is the red, green, and blue channels. And when you look at what happens after it goes through that very first layer, it goes through a whole bunch of convolutions. I think, what did we say? It was, 64. We're only showing the first 4 channels, not all 64 channels. But these are the first 4 channels, and this is after going through the convolutional layer as well as the ReLU activations. And you can see that these feature maps that we get, first of all, they're smaller than the original image. Well, maybe they actually, let's see. I think there was also maybe some max pooling. But qualitatively, they still look kind of like an elephant. Not exactly, but you can sort of see a resemblance. However, as you go down the layers, and if we look at what comes out of layer 10, here you can see that we've done a lot of layers of max pooling, and so finally, these are probably, I don't know, maybe 16 by 16, or they're relatively small images. And at this point, even though this is technically spatial information, it doesn't really look anything like the original image, because we're sort of on the way transforming that image to features that are useful for classification. So as you go deeper and deeper, it looks less and less like the original image, and the information becomes more and more specialized to this classification task. And at some point, after we get to the end of our convolutional section, then we just flatten these things and we just put them in as these raw features into our dense network. And at that point, We don't really think of them spatially at all. Okay, so this is just kind of peeking inside BGG and looking at what comes out of the different layers. All right, any questions? Okay, great. Okay, so for the rest of the lecture, I'll just tell you more generally about different applications of deep learning focusing on imaging, and also different kinds of structures, especially ones that you encounter for generative models. So let's first talk about kind of perspective of what we've spent most of this unit on is just one very simple problem within, image processing or machine learning for images, and that's image classification. And as we know, what happens in classification is you get an image, and this image is labeled with one class, one integer, which let's say is cat. And your objective is, out of a whole list of maybe 1,000 different categories of what's in the image, you want to identify that this is in fact a cat image. Okay, but there's a lot of other things you can do. This one we've also talked about, classification plus localization, where not only do you want to say, yes, I believe this is a cat image, but within the image, this is where the cat is. You want to give it a bounding box for that class that you are predicting. So that is, classification plus localization. Now, another thing we could do is you could take that one step further, and you could say, well, what if the image has a whole bunch of different objects in it, not just one object characterizing the entire image, but this image, there's a dog here, another dog here, and a cat here. So still, you might have 1,000 categories, but rather than for the image just producing, one single category and its location, its bounding box, you want to try to identify all the places that any of those categories could appear in that image. So, maybe, I don't know why tree isn't labeled, but you certainly could have tree as another category and put a bounding box there. Maybe you could have like couch, and so on. So this is called object detection. Okay, any questions? Object detection? Okay. Now there's, so if you think about the outputs here, the output of this network is, one single, well, let's say that the goal of the task is to predict one single thing. And here the goal of the task is to predict, again, that there's a cat and then where it's located. And here the goal is a few of these things. When we talk about segmentation, what we're doing is we are looking at, for every pixel in the image, we want to classify that pixel as one category. So for example, in this image, all these green pixels have been categorized or classified as grass, yellow ones as cat, and the purple is tree, blue is sky. So what's very different about segmentation is that if you think about building a neural network, the architecture of the network here has just as many outputs as it does inputs, right? Whereas this guy, we start with 224 squared pixels, but we end up getting an output of 1,000 possible, probabilities. This one, we need a very different architecture. The architecture cannot look like convolutions down to dense. It needs to take in an image, do some stuff, and output an image. And it turns out that the image that it outputs, there's different ways to think about it. You could say that the image it outputs is one hard classifier output per pixel, or you could even have, per pixel, you could have a PMF over the different classes. There's different ways to build it, but it's fundamentally sort of a different network structure. You need a very different neural network for that. So there's something called a UNet, which is a very famous network for that, which does use convolution, and it uses downsampling, it could be max pooling or average pooling, but then it has these skip layers across at different resolutions. And that same UNet, even though it was proposed for segmentation, is actually very useful for a lot of other things that I'll talk about in a moment. Okay, so any questions on segmentation? Okay, and then here we have sort of a combination between segmentation and object detection, almost, where for pixels that belong to a class, you want to identify them, and then for other pixels where you think these are not really part of any class, you just return the pixels, the raw pixels, basically. So it's sort of like a combination between object detection and segmentation. Okay, but they all have sort of a classification flavor because there's discrete labels or categorical variables in all those cases. Okay, so that covers object detection, segmentation. So let's talk about a few other things then that you can do. Image compression. So this is something that traditionally we would use like an algorithm like JPEG to do. But you can also build a neural network to do this, and you can do much better than JPEG. And there's all sorts of image processing tasks, like if you're given a noisy image, can you clean it up? Can you remove that noise without making the image blurry? Keeping the sharp details. Or if you get a blurry image, can you sharpen it? If you get a blocky image, like sometimes when watching television, if there's a problem with the communications channel, you'll notice the MPEG encoder is starting to fail, and you get these little blocky artifacts that show up. So you could build into your television a little deblocking thing that sees that happening and automatically tries to fix the problem so you never experience it. Super resolution, that is where you're given a small image and you want to make it much bigger, but if you did that in the traditional way, it would look kind of blurry once you blow it up. And so in super resolution, you want to make it bigger and you want to restore the sharpness. So similar to deblurring, except the input image is small and the output image is large. Then we have some medical imaging type of technologies like magnetic resonance imaging or computed tomography. Both of these are sort of like you collect data in a different domain. It could be the Fourier domain or in the radon transform domain. And then from that data, you want to construct an image. And often in these cases, what you do is to speed up the sampling process. You collect a lot less data than you would otherwise need. And in order to fill in the missing details, you use deep learning to do that for you. So in MRI, you might collect only a quarter of the measurements or even less than the Nyquist sampling theorem tells you need, because that will, you can basically keep patients out of the scanners, otherwise the MRI exam can be very long. So for patient comfort, and also because these machines are very expensive in a hospital, you want to get as many patients through the machine as possible. That form of undersampling is important, and then deep learning is basically the state-of-the-art technique to extract those images from those Fourier measurements. Another problem is inpainting. So maybe, we have a picture of a cat, and what I do is for whatever reason, I don't give you those pixels, and then ask you, can you please fill in that box? And it will, using the information around it, try to figure out what is in that box there. Phase retrieval is another one where you observe Fourier measurements of some spatial signal or temporal signal, but for whatever reason, you cannot construct the phase. All you get is the Fourier magnitude, and then your objective is to somehow recreate the phase. That shows up a lot in microscopy and X-ray applications. The DNA double helix was discovered using phase retrieval. And then finally, image generation, which I'll talk about a little bit more in the next few slides. So there, the objective would be, can I build a deep network that just generates cat images? And I want them to be as realistic as possible, or whatever images you want. And these are just, imaging applications. Obviously, we can do a lot of things outside imaging. And we've been focusing on convolutional neural networks. I mentioned the UNet, which is also convolutional, but it gives you output same as input size. There's all sorts of other networks. Recurrent neural networks are sort of like you have a neural network like we've talked about, but then there's some sort of feedback where the output of the neural network is fed back into the input. And those were how people were looking at language models a long time ago, and then they noticed that they didn't really have enough memory to learn long sentences, and so that was improved with these things called long short-term memory networks. But eventually, people moved away from those and have been using transformers, which is a totally different architecture that's not convolutional. Okay, any questions on anything in this page? Okay, so let's talk about a few different structures or concepts that you may have heard of. Autoencoders or variational autoencoders. So these are networks that have two parts. There's an encoder and a decoder. And you start with an image and, for example, or it could be something else, but we'll say it's an image. And what the encoder does is it comes up with a representation of that image that's much lower dimensional. Basically, you try to, so it comes up with these low dimensional features describing the image, and then the decoder tries to map them back up to the original image domain, and you train the encoder and decoder perhaps just based on mean squared error loss between input and output. So what it's trying to do is it's trying to figure out, is there a way of squeezing the information for this distribution, what I've trained on, down to a relatively few numbers and then back up again. And there's a lot of applications for why you might want to do something like this. So on one hand, this looks kind of like compression. It's like you start with this big image and you boil it down to a smaller list of numbers. Perhaps you could just store those. So you could think of it as compression or dimensionality reduction. Another thing is denoising. So basically, if you train this network on clean images, and let's say it works reasonably well on clean images, now if you put in a noisy image, there's a lot of extra information in that noise that the network is not going to know what to do with. And so what it's going to do is pretty much strip off the noise and generate the clean image, which are things it knows about that's closest to this noisy one. So it's one way to do denoising. Another thing is you can use it for anomaly detection. So if you train this again on images from one data set, it knows how to deal with those. Now, if you give it an image from a completely different data set, it's not really going to know how to compress it and extract it again. So what you're going to notice is that for that different image, there's going to be quite a big difference between x and x prime, much bigger than for the images in your training set. And so that alone can tell you, okay, this image here is probably from outside my training set. So you could use it to detect anomalies or things like that. And then finally, we can use this for generative modeling. So let me describe the VAE first for that. So in this regular autoencoder, this Z is just, everything is deterministic here. So you take in your image, you put it through your encoder, and you get some pattern of numbers here. You could, as part of your loss, you could try, in addition to minimizing mean squared error, you could say, I want these to be close to Gaussian, zero mean unit variance Gaussian. And then if you can do that well enough, then what you can do is you can strip off the encoder, when you're done, and just put in new random Gaussians into your decoder, and you might come out with decent images. A slightly better way to do that is through these VAEs. And in that case, the encoder doesn't give you just a realization. It actually gives you a mean vector and a vector of standard deviations. And then those things are used to scale and shift a random zero mean unit variance Gaussian to get you your Z vector. So this is sort of what the equation would look like. So the input sample goes through the encoder, gives you the mean and the standard deviation vector, and now you multiply the standard deviation vector by these zero mean unit variance Gaussians, and those are going to be your so-called codes that go through the decoder. So from a single image X, you can actually generate a whole bunch of outputs from that. And so both of these are useful for generative modeling, where you train the whole system initially, but then you get rid of the encoder, and you just use the decoder to generate new samples from whatever distribution you would like to generate them from. Okay. Any questions on autoencoders, VAEs? Yes?
Can you repeat the variation of autoencoders once again?
Yeah, so here there's just a deterministic mapping from X to the code, whereas here X gets mapped to a mean vector and a vector of standard deviations. And then you generate random Gaussian codes, and you basically shift them by mu and scale them by sigma to get your random code Z. So that actually means that, like, for a single X, you can generate many Z's and many X primes.
By different scaling?
By different random code vectors here. They all have the same shift and scale because that's deterministically from X, but this is why it's random. Yeah. And these generally work a lot better. People still use these. People don't use the basic autoencoder as much.
And also, like, generally, what is this latent vectors or latent space?
That's a great question. So you don't really know what it's going to be. Let's say I just train it to minimize L2. It's going to try to deconstruct your signal in the way that is best for it and its architecture to minimize L2. However, you can often find interesting things when you start to look. You might notice, like, if you zero one of the Z's, or if you make it big or small artificially, you might notice certain things happening in the output. You might even discover, like, oh, wait, this particular code is controlling whether they have glasses or not, if I'm generating faces, or things like that. So there's interesting work on that. There's things you can do with more fancy losses where you can try to make certain elements of that Z vector correspond to certain traits in an image. You can try to force that to happen if you use the right loss also. Yeah. Okay. All right, any questions? Okay, so these things were kind of state of the art maybe 10 years ago. And then people started getting very interested in these things, GANs, generative adversarial networks. And so here, we have a generator which takes, say, zero mean identity covariance vector to the X domain. So that is very similar to this. This also has the same kind of structure as that generator. But in order to train that generator, the GAN does something very interesting. It has a discriminator, which is basically just a binary classifier, more or less. And this thing is trained so that if X is a real, clean, original training sample, the output is large, or if it's fake, the output is small. For example, if it's maybe, you can put it through a softmax and it goes to 0 and 1. And essentially, you train these two things together, like they compete against each other. So the generator tries to fool the discriminator, and the discriminator tries to police the generator and say, no, I can tell that's real, I can tell that's fake. And so when you start out, neither of them are very good. But as they start training, the generator becomes more sophisticated in fooling the discriminator, but the discriminator becomes more sophisticated in catching the generator. And so gradually, there can be some stability problems in training these two things, but eventually the generator becomes very good at generating images because the discriminator has also gotten very good at discriminating, real from fake. So basically, yeah, does that make sense at a high level? Any questions? Okay. So there's various formulations of this. They evolved over time. They got better. The recent ones, I don't think there's really many stability problems, and they work really well. So these things were state of the art, I don't know, maybe 5 years ago or something. People were very excited about these. And then there was a new idea, normalizing flows. So here we have, let's see, we have, I think this might be a little bit misleading. So I would say, I stole this picture from somewhere else. So you want to think of this, this has like the structure of an encoder and a decoder. However, this latent vector is the same size as the input. It is not smaller in dimension. And this is because this network needs to be invertible. So you start with an image, and you try to drive that to a vector that looks Gaussian, zero mean identity covariance. And because that network is invertible, you can invert it, and now when you want, you generate new Gaussian samples, and from them, images. So you train this thing once, and also because of the invertibility, the training of it can be done without this discriminator. It's just, you can just train it using maximum likelihood. The catch now is that not only does the network need to be invertible, which means there's lots of operations which you cannot use because they're not invertible, but also you have to have a nice way to compute the determinant of the Jacobian of the entire network, or the inverse network. So, so this is itself a... Okay, so usually when we take the gradient, all throughout our class, we've taken the gradient of a scalar. I haven't done a good job of my bold facing, but this is a vector. This is an entire vector. So that means this operation is like the gradient of every element in that vector. That is called the Jacobian. So that's a giant matrix. So that's something that you need a way of computing that efficiently, and that also puts some constraints on how you build your model. So the advantage is maximum likelihood, there's some nice stuff, but then the disadvantage is you're quite constrained in terms of how you architect the system, and people have some ways to do that, but there are some limitations. So, so for a while, people were very excited about these after they were excited about GANs. Any questions on normalizing flows? Okay. But then now everybody is really excited about diffusion models for, I would say, the last, I don't know, maybe 3 years or so. So in a diffusion model, all these models kind of are similar, and what they try to do is they try to map Gaussian noise to images or whatever you want to generate. What a diffusion model does, it's different from these last few, is rather than doing things in one step, like all these models, it actually breaks up that task into many steps. It might be 1,000 steps. And so it basically, okay, so this is the way to think about it. Imagine that you have a clean image. What you can do is if you go in this direction, what we're doing is we're adding a little bit of noise to that clean image over one step, adding a little bit more noise, a little bit more noise, a little bit more noise. After you do that 1,000 times, This thing looks like pure noise, pretty much. And so this is called the forward process. Now, what you do is, with that forward process in mind, you train a model that tries to invert this. You try to go backwards by feeding in pure Gaussian noise. And what you do is, little by little, you try to do a little bit of denoising, a little bit of denoising, a little bit of denoising over many steps. And finally, hopefully, at the end of that, you get a clean image. And you actually just use one network to do that, but the network knows what step you're at. T is an integer, in this case, let's say between 0 and 1,000. And so you tell the network, I'm at this step, and it says, okay, then I want to remove this much noise. And these things seem to be the best way people know today how to generate images or other data. So, questions on that idea? So essentially what you need to do to train is you just need to train a denoiser, which is a network that somehow removes a bit of noise from an image, makes it a bit cleaner, and you just apply that over and over and over again. Okay. Is that idea clear or clear enough? Yes?
How does the prompt work into it?
Okay, good question. That's what we'll talk about next. So there may or may not be a prompt. So if all you want to do is generate face images, you don't need any prompts. But if you have some side information, and you say like, in this example, you have a sentence that says, I want to generate a photo of a Shiba Inu dog, blah, 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 blah. So what you can do is you can sort of inject into that denoiser network some other inputs, some other features that it knows how to interpret. And it starts out from pure noise and then that prompt, and it says, okay, I want to make that noise cleaner, but I'm going to try to generate something closer to the prompt. And then over all these reverse diffusion steps, the image gets nicer and nicer and nicer while still obeying that prompt. And it doesn't need to be a text prompt. It could be, for example, if you want to do magnetic resonance imaging, it could be the Fourier measurements. That is what you give it at every step of the diffusion process, and then finally it generates samples of what the image could be that was measured in this MRI machine. So the side information you can give it is quite general. You just need a way of building a denoiser that takes in that information and kind of fuses it with the images itself. So it's a very, very general idea. You can use it for a lot of stuff. But yeah, that's how these, and there's probably some newer ones, but at least for a few years ago, these were like the main text plus image generation models. Now, of course, you can do this with videos too. You just, instead of images, these are now 3D, space, time things. So just a matter of being able to train that denoising network on whatever data you have. Okay, any questions? All right, so I think that's it for this unit. Happy to answer any more questions, but since I just posted, I don't know, do you guys, would you want to start the next unit on trees, or you just want to end now? I can do either. Let's vote of how many people want to go home? How many people want to start the next unit? Okay, I think the go homes have it. So, so on Friday again, you have the last midterm. The last midterm covers units 5, 6, 7, and 8. But of course, there's things we've seen in those units from before, things like maximum likelihood and so on. So, so if you looked at the practice exam or the practice problems, you'll see like some of them mention maximum likelihood. So that's just, a thing that I'm assuming you guys know, but now we're doing that in the context of classification and other tasks with categorical labels. It also covers things like gradient descent and backpropagation, neural networks, but none of the convolutional stuff from this unit. Haven't had any homework or any things like that on it. So, and you're allowed to bring in regular 8.5 by 11 paper, but both sides. So if you just want to take the one from before and write on the other side, you can do that. Or if you want to start from scratch, you can do that too. Any questions on the midterm? Okay. All right, great. We'll see you guys on Wednesday. We'll start talking about ensemble methods.